All right, here's part 2 of 5.4c. The bottom of the page we left off, you'll notice that it asked for displacement, total distance, and it gave you an if s of 1 equals -4 thing. You'll notice that this page after it, called 5.4c, last bit, a fundamental theorem of calculus, it has all those things, has a nice graph, just more space to actually do some work. So we're talking position, velocity, and acceleration again, this time in terms of definite integrals. We have our velocity function, t squared minus t minus 12. You'll notice we have this nice graph over here. Let's see if I factor that really quick. Our x-intercepts are critical values, -3. And I guess it's t-intercepts, I'm sorry, -3 and 4. If we were to look at a number line, -3, 4, positive, negative, positive, that helps us think about increasing, decreasing. Okay, so part A asks about displacement. Please note in part B it talks about total distance. So if we have this graph of v of t, we can figure out where our position function is increasing, aka moving to the right, or decreasing, aka moving to the left. But when we want to find our displacement, the amount of space that we have changed from where you started to where I ended. So I'm going to draw a little picture over here. You don't need to draw this. Here's me. Over an hour, I walk out, I walk back, I walk back to the right, I start walking left again, and then finally I decide, you know what, I'm going to stop right there. So think about this path that I just took. What is my displacement? Displacement refers to the change in position from where you started to where you ended. This right here is displacement. It takes into consideration moving right, moving left as opposite directions, and only talks about the change from where you started to where you ended. So it considers movement right to be this positive idea, movement left to be this negative idea of distance. And adding positives and negatives together gives you a change from where you started to where you finished. Thinking about this idea, we can calculate displacement of a particle from the velocity function by taking the integral over the interval a to b of v of t dt. That is going to give us our displacement. So for this particular problem, we are going to do the integral from 1 to 5, because that is our interval up there, of v of t dt, which equals the integral from 1 to 5 of t squared minus t minus 12 dt. We're going to do this one by hand, okay? Hope you have some space. The antiderivative is 1/3 t cubed minus 1/2 t squared minus 12t, and we're going to evaluate that 5 and 1 using our first fundamental theorem of calculus, that is 5 cubed over 3 minus 5 squared over 2 minus 5 times 12 is 60 minus 1 cubed over 3, that's 1/3, minus 1 squared over 2, which is 1/2, minus 12. Plugging 1 into there. Oh boy, here we go. That looks to be about, let's see, I'm going to do this piece by piece. 125 minus 1/3, so that's 124 thirds. Negative 25 halves minus negative, so plus. So negative 25 halves plus 1/2, that is minus 24 halves. And then finally we have negative 60 minus negative, so plus 12, that's minus 48. Which is, again, I apologize for running out of space here, 124 thirds minus 60, which is 124 over 3 minus 180 over 3, which is negative 56 thirds. So that is how many units away from where we started to where we're located. We moved 18 and 2/3 units to the left. To the left. Okay, what is the difference then with total distance? Back to my picture up here. Even though my displacement was only this much right here, I certainly did a lot more walking than that displacement is. I walked all the way over here, and then I walked back, and then I walked all the way over here, and then I walked back, and then I walked all the way over there. How do we consider this? How do we figure out how far the particle has moved in total? Well, that would have to get rid of this idea of moving left and moving right. If we took this chunk and laid it out that way, and we took this chunk and then laid it out that way, and this part and laid it out that way, it's essentially trying to get rid of this idea of left and right being different, left and right being plus and minus. We need them to be the same if I'm going to calculate my total distance traveled. So to get total distance, you take the integral over your interval of the absolute value of v. This is a little bit harder to deal with by hand because you now have to think about the integral where it's positive and where it's negative to do by hand. A calculator can do this really well for you, but I'm going to show you how to do this one without a calculator this first time through. So for our problem, that would be the integral, or total distance would be equal to the integral from 1 to 5 of the absolute value of v of t dt. So why did I make that sign chart up above? This is going to help me. Everywhere up until 4, our function is negative. I don't want to consider that function being negative. I want to think about everything being the same sign or positive. So what I have to do is I have to break this integral up into two integrals. One from 1 to 4 and one from 4 to 5. Now, here's the thing. If we take the integral from 1 to 4 of v of t dt, that's going to give us something negative. I don't want something negative. I want my total distance. I want everything to be positive. So what we actually have to do is, because this signed area that this integral is going to find is going to be negative, we actually need to take the opposite. So I'm actually going to have the negative integral from 1 to 4 of v of t dt. And then we're going to add that to our integral from 4 to 5 of v of t dt. So that would be negative, we did that antiderivative already, 1/3 t cubed minus 1/2 t squared minus 12 t from 4 to 1 plus our antiderivative 1/3 t cubed minus 1/2 t squared. I forgot my squared over here, I apologize. Minus 12t from 5 to 4. I'm going to wave my hands a little bit and say that this is equal to the opposite of negative 45 halves plus 23/6. Again, a little hand waving, which at the end when you add it all together is 79/3. A little bit more challenging to do. A little bit more challenging to do by hand with these absolute values for sure, because you have to figure out what part of your graph up above is going to give you negative area that we don't want negative area for. We need to take that thing that I just colored red and flip it over, and how we do that is we take the opposite of the integral. Okay, last question. If s of 1 equals negative 4, find s of 3. This sounds like an initial condition. Let's think about this. These ones are sometimes hard to do. If we were to integrate our velocity function from 1 to 3, why would I choose 1 and 3? Because that's the stuff it's asking about. If I were to integrate v of t from 1 to 3, that would be v's antiderivative, which is our position function s, and using fundamental theorem of calculus, that's s of 3 minus s of 1. So how are we going to solve for s of 3? Well, s of 3 is right there. If we move s of 1 to the other side, we get s of 3 equals positive s of 1, because we have to add it to both sides, plus the integral from 1 to 3 of our velocity function. So this is something that's going to be very important. This happens all the time, where we have the function at some value is equal to the initial condition. So the function at another value plus integral from another to value of that f prime of x dx. So that actually gets used quite often. But anyway, back to our problem. How are we going to find the value of s of 3? We need the value of s of 1, which happens to be -4, but now we have to actually integrate v of t, which one more time, 1/3 t cubed minus 1/2 t squared minus 12t, this time from 3 to 1. So please note one more time, that's there, that's there, that's there, that's there. You'll notice that pattern often when we have to do these things. And again, finally, a little bit of hand waving, -4 plus, and I'm just going to tell you that I got -58/3 when I did that, and that is equal to -70/3. That is our value of s of 3. So on Monday, you'll have some time to practice these things. I will be back on Tuesday, and we can go over any questions that you have then.